I need to be in there.
You're the pretty face, man.
Okay, all right. That's what I'm here for.
Sí, Eric es la cara bonita. Okay,
Are you hitting on me? Your wife right there.
Well, no longer. I can't do that any longer.
I'm not your wife longer?
No.
Yeah, something that he's been meaning to tell you.
Le doy la página 3 del examen de física a mi amigo Eric, graduado de física de la UCLA. UCLA. Bueno.
Immediately don't like it. Ooh, oh, okay, all right. Número, what is it? 14. It looks very interesting.
You're talking about 10? Oh, 14, okay.
But we'll get there. We'll get there when we get there. We'll get there when we get there.
Eric le gusta 14, pero bueno.
Although, oh man, I see a lot of circles.
I picked this up in internet.
Well, the first page, the circle problem was pretty cool.
Yeah.
So maybe.
Maybe. But I didn't circle 14 this time.
That's very sad. All right, so looking at número 10. Calculate aproximadamente. Yeah. Aproximadamente la energía. Is that how that's pronounced? Energía. Right, the G's. I'm still messing up there. Cinética máxima de un electrón emitido desde la superficie. Is that, yeah? Superficie de una plaza metálica. Placa metálica. Cuando incide sobre ella un haz de luz.
Light beam.
All right, that makes sense. De cierta frecuencia, cuya energía es 5.3, so 5.2 electron volts. Consider la función trabajo de la placa igual a 4.3 electron volts, donde the 1 electron volt is this much. Okay. All right. What is this actually saying? Calculate the energy, the kinetic energy, the maximum kinetic energy.
The maximum kinetic energy
of 1 electron that's emitted from a surface of a metal plate.
Yes.
When something?
When you shoot a light beam on it.
Oh.
Sounds like the photoelectric effect.
This is the photoelectric effect, which is not a difficult thing to do usually. I mean, like, it's a linear function.
Oh.
It's a linear function.
Interesting.
So it's not...
It's probably just a plug and chug one.
Yeah, there is some, like, this kind of question is good because, like, there's some amount of innate knowledge you need to have. Right? So, like, you need to remember, like, oh, the work function represents this, blah, blah, blah.
Yeah. That's why this test is hard. You
have to have it memorized.
So many formulas. Yeah.
That one's a reasonable one because, like, once again, it's like HF plus, was it phi? Is equal to work done.
I believe you. You're the physicist.
Okay. Someone in the comments will correct me.
Alguien en los comentarios. ¿Está correcta esta fórmula?
Okay. So, I mean, like, maybe we'll come back to it, but probably not. Probably not. We'll probably not do that one.
Okay.
So...
11.
Okay. So, por 11, un objeto de un objeto se aproxima con velocidad constante a lo largo del eje óptico de un lente convergente cuya distancia focal es 20 centímetros. Si el objeto pasa de una distancia medida, ¿qué es medida?
Measured.
Desde el vértice de la lente de 100 centímetros a otra de, what is this one? 30 centímetros en un intervalo de tiempo de 4 segundos.
5.
Oh my god. I should really know that. Stop that. All right. Determine la rapidez promedio con la que se desplaza la imagen.
Interesting.
Okay.
That's interesting, and I'll tell you why in a moment.
Yeah. This is an optics problem of some kind.
Definitely.
Are they asking about what's well, I see lo largo del eje óptico. That's a mirror, right?
The optical axis. It
The
says
optical axis.
an object is getting closer to.
Oh, it's approaching.
Yeah, it's approaching a lens, I think,
Okay.
with constant speed
Mm-hmm.
along the optical axis of a converging lens.
Okay.
It's interesting.
No, I'm not gonna draw it. Because
not
we don't
yet,
know.
not yet.
We don't know
if this is the one you.
We don't know if it's plus. Like I can't remember how to do.
This problem
That kind of
is
stuff.
weird. Like lenses. I think this is the first time I see lenses and speed, like an object.
Yeah, lenses and speed at the same time is very strange.
That's cool.
What is Kuya?
That's cool. Kuya.
Okay, so it's saying like you were approaching this converging lens whose optical focus is 20 centimeters.
Focal distance is 20 centimeters.
Okay. If the object passes that distance, the 20,
A certain distance.
a certain distance.
Yeah.
Medida,
Measure
of vertice. Okay, help me out here. I don't know what this is.
It says the object is moving a distance measured from the vertex of the lens.
Okay.
Oh, and then they're saying the distance is 100 centimeters to a new distance of 30 centimeters in a time interval of 5 seconds. Okay. I think I get it.
I get it, but why?
Yeah. It's like remembering lens formulas.
Yeah.
You know, converging, diverging is already a lot.
Oh my god. Yeah,
On top of the
dude.
whole. Yeah. Okay.
So what are they asking? What ultimately?
They're asking for the average speed.
Oh, of the image, not of the particle of the image.
Yeah.
Oh my god.
That sounds hardcore. Wow. And calculus is not even required for this test.
No, yeah, calculus. This doesn't need calculus. What it
doesn't.
does need is for me to pick up my phone and
look up the formulas.
The formulas, because I cannot remember those to save my life. All right. To make sure that this video doesn't go on forever, we'll skip around a little.
Yeah. Okay. 12. Well, we can talk about 12 a little bit. It's all about linear dilation.
Oh, okay. Of a metal. Dilation.
Metallic.
Okay, based on temperature.
Yeah.
Okay. I mean that's a plug and chug type
Wires.
problem.
13 is your favorite problem.
I guess
It's really not.
It's
like
what is it? Numero 13?
13.
It's about God, what are these called? Capacitors.
Yeah.
So capacitors simply have the opposite rule of resistors.
Yes.
And that can be pretty easily proven with Kirchhoff's laws, but
Okay. Oh wow.
we're not going to get into it. Well, we might get into it, but
It's
I
when
wanted.
Number 13 is probably also the easiest of all the exam.
Oh, really?
It should be. I mean,
It should be the easiest for sure. Especially since they put the numbers as 1, 2, and 2.
Yeah.
Okay. Número 14.
Okay.
I do want to read this one.
Let's do it. Okay. Número 14, por favor, Eric.
Got it. Alright. Un rayo de luz incide desde de aire con un ángulo de 45 grados por una de las caras de un cubo transparente. Calculé, I'll do this word again. Aproximadamente
Muy bien.
el índice de refracción del cubo da la condición de que cuando el rayo de luz incida sobre la cara interna adyacente, lo haga con el ángulo crítico según se muestra en la figura. Okay, I actually think I almost completely understand what's going on.
Oh, wow.
In the problem. I probably want to jump on this one. We'll look at 15 because but this will probably be the one that I do from this page.
Sounds good.
I think so.
A Eric le gusta la 14, pero vamos a ver la 15 ahorita. A ver la 15. Por favor.
Okay, 15. Una bobina circular de 3 centímetros de radio tiene su sección recta perpendicular a campo magnético de 4, it's probably Teslas, right?
Tesla.
That's Teslas. Calculé el really struggle with it. Flujo magnético in, is that gonna be watts?
I think that's Weber.
Oh my god. Oh yeah. Down here. Alright, got it. A través de la bobina. ¿Qué es bobina?
Coil.
Coil. A circular coil with a 3 centimeter radius. Oh no. Is this a flux problem?
Yeah, this is magnetic flux. This is electromagnetism, and
No.
they have like 50 formulas you have to memorize.
The flux ones are always like, I don't know. They take like 50 years. They're like so ridiculous. They seem so simple, always, and they never are. So no, I'm not going to.
Okay.
If I had prepared ahead of time, that would be a fun one to do.
That's fair.
But that's not one that I'm gonna do just on first watch. Absolutely not.
Okay, makes sense.
But going back to 14.
14. Ya, vamos a hacer la 14. Bueno, Eric lo va a hacer.
Thank you.
Okay.
Okay, I think I see words here that I'm pretty sure I understand what's going on. Ángulo crítico, critical angle, right? Is there interna adyacente?
Adjacent internal phase.
Okay, right. And yeah, so this I believe is just talking about a case of internal refraction. So I'll draw it out. It'll make more sense if you look at the board. But I have to actually try to draw a square. So don't judge me. Okay, that's not that difficult.
Okay.
What is this angle? What?
Nada. Muy bien.
Oh, I guess I should do this. I should do that. And then, so this is, ¿cómo se dice? Rayo de luz. Boom, boom, boom.
Rayo de luz.
So this is pretty important to talk about. So let's see. We call this. I don't know how you would say it in Spanish.
It's internal refraction, right?
Yeah, internal refraction. So
Refracción interna, me imagino.
go figure. So internal refraction is always going to be when the ray of light is parallel with the surface, like when it either enters or exits depending on what's going on. So something to think about when you're doing all these questions and you're looking through these, they're not going to tell you like, oh, when it's 90 degrees, they're going to use like words like total internal refraction or something like that, right? So it's just one of those ways that can kind of like sprinkle extra little tricks. They don't, like, at no point do they mention this is 90 degrees.
Right.
This looks like Snell's law.
Snell's?
And they want us to find what the index of refraction, I was thinking, that's our unknown. That's the thing we care about. We are assuming outside is air. I believe they say that.
Yes.
Outside is air, right? So air, I think, has like some ridiculous index of refraction. Something like, I don't know, 1.002, I don't know. Something like that.
Okay.
So I think we're just going to call it 1. I think we're just going to call it 1.
We're physicists here. We approximate all the time.
That's correct.
There you go.
So a reminder of Snell's law. So if I have a surface, and so like let's say like on top is like air, and on the bottom is water, agua, we would have an incident ray of light change its angle. So theta 1 versus theta 2. So the angle will change depending on the index of refraction of each.
Y el ángulo se mide desde esta línea vertical.
You're gonna have to say that. But I'm sorry.
So do you always measure these angles
From the normal, yes.
The normal. Okay.
From the normal of the surface. That is correct.
Okay, cool.
That is correct.
Cool.
So the relationship is always like if this is material 1, this is material 2, it'll always be N1 sine of theta 1 is equal to N2 sine of theta 2.
Beautiful.
So it would be pretty easy if they just told us like, oh, the angle here is whatever. But we have like this sort of 2-part thing where we have this happening twice with like sort of a strange situation going on over here. And so like there's a little bit of a wrinkle in that like we have like 2 different index of refraction situations, 2 different Snell's law examples.
Okay.
I'm assuming we're gonna have to like do some geometry. I think
Nice.
we're gonna have to do some geometry.
Nice.
Unfortunately. Okay. So if I look here to start, why don't we just do the geometry first? Let's just get it out of the way.
Okay.
Because I'm gonna have a real hard time otherwise. So let's see here. This is not the same angle as this. That's the whole Snell's law situation. So even though I drew it and it looks like that, it's a wider
Otherwise,
angle.
that would mean these materials the same as there. Right?
Yeah, that's exactly what it means. So, okay. Let's call this angle phi. Let's call that phi. So that would mean that this angle here is 90 minus phi. Okay. And then this angle here is 90. So we have an unknown that we've kind of added to the whole problem in order to do this. So we got to deal with phi at some point, but for now we kind of need it because we have no information about the internal angles here in this triangle. Okay, let's take a look specifically here. We've got index of refraction of air, which I'm just gonna say is 1, sine of 45 degrees, which has a relatively nice value, is equal to an unknown n with an unknown angle.
Looks good.
Yeah, so you guys better know that out there. You guys better know that one.
I think most people will.
If you don't know your unit circle, this is like the call. This is the sign that you need to know the unit circle. Okay, so that's just for up here. So for this, because this is 90, with our critical angle or internal refraction, whatever language we're using. I think they said critical angle. They said, I believe so.
Yep.
Yeah. Okay. So let's see here. I'll say this side has the unknown n, sine of 90 minus 5. Oh man, I did not give myself any room. I'll fix it. Don't worry, guys. I'll fix it. Okay. All right. 1 sine 90. Great. Wonderful. This is just cosine, right?
Yeah, cosine of phi.
Okay. More trick. Okay. So we have phi. How do I want to mess with this stuff? Diego, you have any pointers for me?
Cosine theta. Well, you could use the Pythagorean identity.
Oh my god.
That's one way to do it.
Yeah, that seems like a good idea. God, I feel so stupid. I cannot believe I didn't think of it. Okay, so we have cosine squared, sine squared, so we do know okay. Alright, so let's go 1 over n squared plus 1/2. 1 over 2n squared?
Yeah.
Okay.
Good.
It's equal to 1. So this is 2 over 2n.
Yeah, combine. Very nice.
I feel like we're basically there, right?
Very nice. And n cannot take on negative values, right?
No, n cannot take on negative values. I think n cannot take on values less than 1.
Interesting.
I believe the vacuum of space is an index of 1.
Okay.
I believe.
It's good to know. That's a good reminder.
So n is equal to... I'm not rationalizing. I refuse. Unless they make me.
Well, I guess you can.
What? How's your mental math? How's your mental math?
Not good when you have roots like that. Are you gonna pull it up? Okay.
I'm gonna try. Yeah.
I think in this exam they give you a very simple calculator.
That could do this sort of.
That
business,
can
yeah.
take, yeah,
Okay.
the basic operations plus square root. So you can do this on the calculator. Beautiful.
Which is B.
Nice.
Okay. There we go.
It.
Done. Okay, not so bad.
Yeah, very good video. Me gustó. Hace tiempo que no veía la ley de Snell. Y bueno, fue un bonito problema para mí. Espero que a ustedes también les haya gustado y suscríbanse.
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 Suscríbanse.